Assalamualaikum and salam sejahtera. So let's continue our lecture by subtopic 5.2. The topic is energy and conservation of energy. So according to the learning outcome, students should be able to state the principle of conservation of energy, then apply principle of conservation of energy. We are focusing on mechanical energy and heat energy due to friction. Then state and apply the work energy theorem. Alright, so let's start by the first part, which is under energy. We need to know what is energy. So energy is defined as the system ability to do work. The SI unit for energy is same to the unit of work, which is joule, or the symbol is capital J. Energy is under scalar quantity. So remember, we are discussing about magnitude only. There is no direction. Let's start by the first type of energy. We are discussing about the potential energy, where the symbol is capital U. So what is potential energy? Potential energy is defined as the energy stored in a body or system because of its position, shape, and state. Three factors influence the potential energy, which is position, shape, and state. Why? Because actually there are three different types of potential energy, which is gravitational potential energy, elastic potential energy, and electrical potential energy. For this chapter, we are focusing on two types of potential energy only, which is the gravitational potential energy and elastic potential energy. Okay, let's start by the first type, which is the gravitational potential energy. The symbol is UG. So what is UG? Okay, UG is defined as the energy stored in a body or system because of its position, where the equation is UG equals to mgh, or we may simplify it to be U equals to mgh. So the potential energy now depends on, okay, m, G, also H. So what is that? So M is the mass of a body, G is the acceleration due to gravity, and H is the height of a body from the initial position. So according to the first point before, the potential energy depends on its position. So here we are discussing about the position, which is height. So U and H, they are directly proportional. By increasing the height, the potential energy also increase. Okay, the gravitational potential energy depends only on the height of the object above the surface of the Earth. Of course, by having the same body, and then our G still remain constant, then U depends on H. Okay, by changing H, U also change. Next, the second type of potential energy, we name it as elastic potential energy. The symbol is US. So what is US? US is defined as the energy stored in elastic materials as the result of their stretching or compressing. Okay, springs are a special instance of device which can store elastic potential energy due to its compression or stretching. So for this, normally by having changes in length, by compress it or by elongate it, then the energy stored by the object. And for example, for any rubber or spring. So by having changes in length, which is under elongation or compression, then the energy stored by the object lah. Okay, so according to the Hooke's law, okay, Hooke's law states the restoring force Fs of spring is directly proportional to the amount of stretch or compression, which is extension or elongation, X if the limits of proportional is not exceeded. Alright, so according to Mr. Hooke, okay, the idea is the restoring force is directly proportional to the elongation or compression. Okay, so X representing the displacement lah. So they are directly proportional, but it just in opposite direction of the elongation or compression. So based on that, mathematically, we may take out the equation which is Fs equals to negative Kx. So from this equation, we know that K representing the spring constant or the force constant, X is the amount of stretch or compression, which is X final minus X initial, and Fs representing the restoring force of spring. Again, negative here representing direction only, where the restoring force just in opposite direction of the change of length. Okay, so this is the point. Negative sign in the equation indicates that the direction of Fs is always opposite to the direction of the amount of stretch or compression, which is extension X. Okay, let's start by the first case given here, which is under vertical spring. So what do we have? The spring is hung vertically and it is stretched by a suspended object with mass m as shown in figure below. So what do we have? This is the spring, the original one. The spring just at rest. There is no elongation yet. Okay, so by hanging a body, what happened? The spring become longer, isn't it? So we are talking about the elongation of the spring. How do you get that? By hanging a body, the weight of the body just be like this. It just directed downwards. So by elongate the spring, the restoring force exerted now, which is Fs. So remember, Fs, it must be opposite direction of X, isn't it? So the spring just elongate here. So X is directed downwards. So based on this, as we know, vector, okay, we are discussing about the magnitude also direction. So in this case, Fs is positive because it's just directed upwards. X and W just negative because both of these forces just directed downward. So how do we get the equation from this? All right, so let me show you. Okay, according to this, under equilibrium, sum of Fy equals to 0. So two forces exerted now, which is Fs and W. So Fs is upward, so it must be positive, plus W, which is downward, so negative W equals to 0. So that Fs equals to W. So what is W? W equals to mg, which is weight, isn't it? So that from this, the equation getting now should be, okay, Fs equals to W, which is equals to mg. Okay, you may refer to this video, okay, using this link. I think you may understand it very, very well later by watching the video. Okay, next, for the second case, we are discussing about the horizontal spring. So what do we have now? The spring is attached to an object and it is stretched and compressed by a force, F, as shown in figure below. All right. So this is the situation. So there are three different situations given. Okay, for the first one, see, the spring just elongate here. To elongate the spring, the external force should be applied on the object now. So the external force is directed to the right, which is the red one. So by elongate the spring, what happened now? Okay, the elongation now, so the length just increased. So X representing the elongation. So X also directed to the right. So by elongate the spring, remember the force taught by the spring, which is our restoring force. So the restoring force is directed to the left, which is the blue one. So based on this situation, the external force is positive because it's just directed to the right. And the restoring force just negative here because it's just directed to the left. Okay, X also positive because X also directed to the right. Okay, and then for the second part, okay, under equilibrium position, okay, what does it mean? The spring doesn't compress or elongate here. So we are talking about the original length of the spring. So without any elongation or compression, so there is no restoring force, okay, stored by the spring. All right, so in this case, X0, Fs also equals to 0. Next, for the third one, by compressing the spring, what happened? The spring becomes shorter, isn't it? All right, so now X representing the compressing of the spring. Okay, so Spring becomes shorter here. Alright, so the rate force now is our external force applied on the system. So the external force just directed to the left, it must be negative. So by compressing the spring, what happened? The restoring force stopped by the spring. So in this case, the restoring force just directed to the right against X, isn't it? So Fs is positive. Alright, so what is the question getting from this? Okay, so for the first one, what do we have? Okay, sorry. Okay, according to the first situation, okay, sum of Fx equals to 0. So in this case, the external force is directed to the right, so it must be positive, plus the restoring force, which is directed to the left, it must be negative, equals to 0, giving you Fs equals to F. Or from the third figure here, okay, still the same, sum of Fx equals to 0, and then what do we have? Okay, Fs is directed to the right, so positive, plus the external force now is directed to the left, so negative F equals to 0. So still the same, Fs equals to F. Alright, so this is the equation getting from this situation. So the main equation here is, alright, Fs equals to F. So what is F? F is our external force or applied force. Okay, and then for the calculation, remember, according to the Hooke's law, which is F equals to negative kx, in calculation, okay, we just refer to its magnitude only. So the equation is Fs equals to F, which is equal to kx, where F is the applied force, alright, and k is the spring constant, and the unit of k is kilogram per second squared or Newton per meter. So in this case, from the Hooke's law, without negative sign, a restoring force against extension of the spring, okay, X graph is shown in the graph below. Okay, before that, remember, for any calculation, we just ignore the negative sign. Okay, we just refer to its magnitude only. Alright, so by giving you F against X graph, okay, how do we get the equation of potential energy or elastic potential energy? Alright, so according to F against X graph, the area under the graph now representing work. So according to the graph now, we are discussing about the triangle, isn't it? The area equals to the area of triangle. So from this, we may calculate the area using the equation of half Fx1. Okay, half Fx1 representing the area of the triangle here, which is equals to the work done. Okay, so according to Mr. Hooke before, F equals to Kx. So we just expand the equation to be like this. What do we get? Half equal to Kx1 times x1. Okay, so Kx1 equals to F, according to the Hooke's law before. Then you will get W equal to half Kx squared. Alright, so at the same time, the work done now representing the energy stored by the spring. We name it as the elastic potential energy. Okay, you may refer to the link given here. Again, by watching the video, I think you may understand it very, very well. Alright, so from the F against X graph, the work done to stretch or compress the spring is equal to the elastic potential energy US stored in the spring. Okay, therefore, the equation of elastic potential energy US for compressing or stretching a spring is given by W work equals to US, which is our elastic potential energy, equals to half Kx squared, still equals to half Fx. Okay, so by giving you K, we may use the first equation. By giving you the force, also the elongation, then we may use the second equation, which is half Fx squared. Alright, okay, next we just turn to the second type of energy, which is the kinetic energy. The symbol is capital K. So what is kinetic energy? Kinetic energy is defined as the energy of a body due to its motion. Alright, the keyword given now is motion. So for any moving object, okay, the energy contained by the body is the kinetic energy. Okay. Alright, so what is the equation of kinetic energy? The equation is K equal to half mv squared. Against, what is m? M representing the mass of the body and v representing the speed, okay, of a body. Alright, so remember, kinetic energy also under scalar. So we don't have any direction. Okay, we are talking about magnitude only. Alright, next, let's discuss about the principle of conservation of energy. Okay, what is the idea? So the principle of conservation of energy states, in an isolated or closed system, the total energy of that system is constant. Alright, so what does it mean by closed system? Okay, means that there is no external force exerted on it. Okay, free of external force. Then the total energy of the system is constant. So according to the principle of conservation of energy, okay, we may say that sum of E initial equals to sum of E final. So remember the type of energy here, what do we have now? Just U and K. So the total initial of the initial of total energy equal to the final of total energy. Okay, so as we know, the energy is U and K. So U stands for potential energy and K is the kinetic energy. So initially, what do we have? K initial and U initial. And finally, what do we have? K final and U final. So based on this principle, total of E initial equals to total of E final. So what do we have? K initial plus U initial equals to K final plus U final. So by expanding the equation, what do we get? Half mu squared plus mgh initial plus half kx initial squared equals to half mv squared plus mghf final squared plus half kx final squared. Alright, so don't forget for the potential energy, okay, we are talking about two different types of potential energy, which is elastic potential energy and gravitational potential energy. So by discussing about spring, we just take out this. By talking about change in height, and then we are focusing on mgh. Alright, let's say there is no spring involved, so we just cancel out half kx squared to be 0 here and here. Alright, so this is the way. Alright, so again, okay, we just give you some link here. So by watching the video, okay, you may get some knowledge here. Okay. Next, let's discuss about the work energy theorem. Okay, what is all about? So work energy theorem states that the work done by the net force on a body equals the change in the body's kinetic energy. Alright, so what is the keyword? The first one is work done by the external force equals to the change in body's kinetic energy. Okay, so the keyword is work and the change in body's kinetic energy. Alright, so what does it mean? Okay, so now, okay, let's consider a block with mass m moving along the horizontal surface, which is under frictionless surface, okay, under the action of a constant net force. F net undergoes a displacement s. Alright, so what do we have? There is a body which is moving on a frictionless surface. So by applying the net force here, that one is our external force lah. So the object is moving with displacement x. So in this case, according to Mr. Newton, F equals to ma. So the total F exerted on the body is F net. Okay, so F net equals to ma. And then according to the linear motion before, we have discussed about the second equation, which is v squared equals to u squared plus 2as. So by rearrange the equations, you will get a. So a equals to v squared minus u squared over 2s. So by substituting the second equation, which is A, into the first equation before, substitute here. Okay, what do we get? Alright, so by combining these two equations, or by substituting the second equation into the first equation, what do we get? Okay, so F net equals to MA before, so A equals to V squared minus U squared over 2S. Then the equation become like this. Then we just transfer S to the other side. Okay, we just transfer S to the other side, giving you Fs equals to half mv squared minus half mu squared. So half mv squared representing K final, and half mu squared representing K initial. So giving you K final minus K initial. So from this, Fs giving you work. So this is work, and this is K final, and this is K initial, giving you work net equals to delta K. Alright, or by expanding the equation now, what do we get? Work equal to Fs cos theta. Delta K is K final minus K initial, which is half mv squared minus half mu squared. So this is the work energy theorem. So remember, the work done equal to the change in kinetic energy. Okay, next, let's start by the last subtopic here, which is 5.3. The topic is power. So according to the learning outcome, students should be able to define and use average power and instantaneous power. So you need to know what is the difference between the average power and the instantaneous power. Alright, so let's start by the first part, which is under average power. Okay, the average power symbol is PAV, P average. So what is that? When a quantity of work delta W is done during a time interval delta T, the average power, which is P average, is defined as P average equals to delta W over delta T. So what is that? The work done per unit time or energy per unit time. Okay, rate of work or rate of energy representing the average power. So the average power is often simply called power. Okay, average power and power, they are the same actually. So P average equals to P, which is rate of work, W over T. At the same time, work equals to Fs cos theta. Alright, so the equation become Fs cos theta over T. Alright, and then according to work energy theorem, Fs cos theta is work equals to the change in kinetic energy. So change in kinetic energy over time. And remember, according to the principle of conservation of energy, the change in kinetic energy still equals to the change in potential energy. So still equals to mg delta H over T. Okay, for this, there is no delta H. Why? We just assume that H naught equals to 0. So delta H equals to H final minus H initial, giving you H final lah. Okay, which is mgh over T. Alright, so this is the equation of average power. Okay, next, let's discuss about the instantaneous power. Okay, the symbol is capital P. So what does it mean by the instantaneous power? So instantaneous power is defined as the instantaneous rate of doing work, which can be written as P limit delta T approaches 0 of delta W over delta T, giving you dW over dt. Alright, so remember, there is no changes in time, because delta T approaches 0. So we are talking about a specific or particular time. That is why we call it as instantaneous. Alright, we just refer at certain or particular time. So by considering an object that is moving at a constant velocity v along a frictionless horizontal surface, and is acted by a constant force directed at an angle theta above the horizontal as shown below, the object undergoes a displacement of ds. Okay, so this is the external force exerted on it. This is the angle theta from the horizontal, and this is the displacement of ds. Alright, so based on this, what do we have now? So therefore, the instantaneous power P is given by, so power equals to dW over dt. At the same time, dW equals to F cos theta ds. Okay, from the equation of Fs cos theta. So by having changes in work, little bit changes in work, we are talking about a little bit changes in displacement, isn't it? So now dW equal to F cos theta ds, and then we just substitute into this equation. Okay, what do we get? So the equation become P equal to F cos theta ds over dt, and at the same time ds over dt giving you V. How do we get that? From chapter 2 before, isn't it? So V equal to ds over dt, substitute into this equation, alright, and then you will get P equal to Fv cos theta. So remember in chapter 1 V4, by having cos theta, we are talking about a dot product, isn't it, which is under scalar. So the equation still equals to, okay, P equals to vector F dot vector V. Okay, again, what is F? What is V? Okay, F stands the force, and then V stand, okay, the velocity, stand for velocity. Alright, so theta is the angle between F and V. So again, power is under scalar quantity. We don't have any direction. We are discussing about magnitude only. Again, by having positive or negative values of power, what does it mean? Okay, means that the power just lost or absorbed, okay, or released by the system. Okay, all right, the SI unit of the power is kilogram meter squared per second cube, or joule per second, or watt. All right, and then for the unit conversion, okay, we need to know this. What is the relationship between watt and horsepower? Okay, so 1 horsepower equals to 746 watts. All right. Okay, I think that's all for lesson 5. Okay, so see you again by the next lesson. Thank you. Assalamualaikum.